The next error detection technique is cyclic redundancy check. So in parity check, we have observed that which is based on addition, whereas cyclic redundancy check is based on binary division, is based on a generator polynomial. It produces a reminder, that is CRC bits, which are appended to the actual data. So coming to the steps we are going to follow in the calculation of cyclic redundancy check is, first we consider the data and we append zeros based on the generator polynomial. And next we are going to perform the modulo 2 division and append remainder to the original data. These are the four steps what we are going to follow in the cyclic redundancy check. So here if you consider the data, here the data is 100 100 and generator polynomial is 1101. Its length is 4. Since the length is 4, we are going to append zeros, that is the generator polynomial value minus 1. So here we are going to append 3 zeros to the actual data. Now, after appending 3 zeros, we are going to perform the modulo 2 division. So here if we perform, that is we're going to get a carry of 0. 1 and 1 modulo 2 division is 0. Again 0, here it is 1. So we are going to multiply and coefficient, and finally the remainder value what we are going to get is, where we are left with is 0 0 1. So now this reminder which we obtained 0 0 1 is added to the data. So now this is the transmit code word which we append to the actual transmitted data. And now the transmitted data is 100 100 and 0 0 1. This is the code word and this is the actual original data. Together we are going to transmit and we are going to observe at the receiver. Same, we are going to perform the same operation, that is modulo 2 operation, and we are going to check if the final result is all zeros, that dividing the received data by the same generator polynomial. If the remainder value is 0, it indicates there is no error. And if the remainder is non-zero value, if it is non-zero value, that indicates that there is an error. Mainly the advantage of this CRC is single bit errors, multiple bit errors and burst errors can be detected using CRC. It is very powerful and widely used. So this is one more example of CRC. This is the data and we can see this is the divisor, that is generator polynomial. Now we are going to append the number of zeros that are appended to the transmitted data is the number of bits in the generator polynomial minus 1, that is divisor value minus 1. So here 4, so we are appending 3 zeros and performing the modulo 2 division, and the final remainder is what we are obtaining is 110, that is appended with the data word. This is the data word and this is the code word what we are appending to the actual data. Now along with the data word and the reminder whatever we are getting, we call it as a, together we call it as a code word, and this is the transmitted data what we are going to transmit. And we are going to check if the final remainder value is zeros. Now you can observe in this example, what we have done is this is the actual transmitted data. So when we perform modular 2 division with the same generator polynomial, we get all zeros as reminder. That indicates that the data whatever 1001 we are transmitting is the data without any errors. And if you observe now, this 1 is replaced with 0 here. So now the transmitted bit is data is corrupted. So whenever the transmitted data is corrupted and the modulo 2 division is performed, modulo 2 XOR operation is performed, we can see that the final reminder is 011. That indicates that there is an error, and the data word whatever we have received, we are going to discard the particular data. And that is all regarding cyclic redundancy check. And the next error detection technique is checksum. So in checksum, the data is divided into equal size blocks, and all blocks are added, and the result is complemented, that is one's complement. So we are dividing the data into equal size blocks, that is n bits, and all blocks we are going to add, and for the final result we are going to is complement the final result is complemented. And here in this example, if we consider the data bits, all the data words 1 2 3 4 named are added, and wherever we are getting a carry, this is normal addition only. Wherever we are getting carry, we are once again adding that carry. And for this data now, we are adding the third data unit. This is the third data unit. Again we are performing addition, and this is the fourth data unit. And whatever carry we are getting, we are once again adding, and this is the final value what we got. And the last step is the result is complemented. So this is the checksum what we are getting. Complemented is 0 0 1 0 0 1 0 1. For that the complemented data is 1 1 0 1 1 0 1 0. So this is the complemented data. So now we are going, what we are going to do, along with the original data, we are also going to send the checksum bits. That is 1 1 0 1 1 0 1 0. So these checksum bits are also added at the receiver. So again at the receiver, the same operation is performed. So original data 1 and 2 are added, and whatever carry we are going to get, we are once again appending that carry and adding that. And this is the third data unit, and this is the fourth data unit, and whatever carry we are getting, we are adding that. And here you observe, this is the checksum. So in checksum, along with the data units, we are also sending the checksum bits from transmitter to receiver. So from transmitter, we are going to send the original data and checksum to the receiver. At the receiver, once again, we are adding the checksum and checking if the sum value is all ones. We are going to complement, and we are going to get all zeros. Whenever we are getting all zeros, that indicates that there is no error. Otherwise, when we get non-zero complemented data, that indicates that there is an error. So these are the three different types of error detection techniques. That is, first one is simple parity check and two-dimensional parity check, and next is cyclic redundancy check, and the last one is checksum. Thank you.